So we will look into some of the algorithms on direction finding, but which gives super resolution or high resolution. So to start with, we have an array. That means spatially distributed sensors. So this is exploiting spatial diversity, right? And let's say M sensors, and you have a bunch of sources, right? At some, so source Sk of t. Let's say k sources, capital K. So so k sources, k itself of course is unknown, and arrival angles or directions of arrival are theta 1, theta 2, etc., theta k. So you can see these are unknowns but non-random. Remember, we were looking at earlier non-random parameter estimation. So this is an excellent example. So unknown non-random parameters. And the sources, of course, itself is, each of these sources is in general, it's a stochastic source for various reasons. Even if it is a single sinusoid, it will have an unknown phase in it, making the whole thing, so that's the simplest case. In any case, we will assume that the sources are, they have some amount of power. So source powers are Pk. And they also have some correlation. So let's say all of them are zero mean, then the correlation is this, right? Yes, this is the correlation, right? This is the, so here we are going to, we can have three different cases. So this is the uncorrelated case, right? If the correlation, so the sources are not correlated with each other. And the other extreme is all the coherent situation. And then, of course, in between you have, this is partially correlated. So you can imagine, in all these cases, we will want to know how to estimate the directions. Of course, the directions of arrival are also unknown. The power levels are unknown. The correlations are unknown. Everything is unknown. So what is known then? Yeah, you collect the data. So this is passive sensing problem. In active sensing, what will happen is you will have a transmitter, and that will transmit, and then you receive. I mean, the transmitter could be the same array as in radar, or a dedicated, that itself could be a dedicated array so that you can form. Remember, last time I showed you how to do beamforming using sensors, right? So you can imagine the same thing. If you want to illuminate in this direction, you have an array here, and you project power in that direction. Then it, of course, gets reflected from whatever is out there. then you collect the data. So this is the data we are going to collect. So we went through this last time. Remember, the advantage of using an array is that you can get duplicate information about the same source, but delayed depending on the angle of arrival and the distance between the sensors. Right? So the extreme narrowband case, the source will have information like this or structure like this. So here, of course, you can see absolute value squared is pk. So this means this is at some carrier omega k or omega naught, some common carrier. So, but around that, the information is spread out here on like phase modulated signal, like in the voice and so on. Now, this itself it could be so narrow that you can assume for during the duration, maybe this is slowly varying compared to this, that it just behaves like a random phase. It's possible, right? Remember, you're not going to sit there and look at this information forever. You're only going to look at it during processing time, or the data may be sampled, so in between. So this is the simplest model. If it is wideband, then of course this narrowband assumption is not possible, and here you will have to consider a significant bandwidth, which another way to say is that, so here you can, as I explained to you last time, if you have a delay here, so since this is the rapidly varying quantity fast time, this delay essentially comes out as a phase difference, right? So this is the key for narrowband. If it is wideband, a delay is a delay. So if we want to bring the delay as a, look here, if we want to bring this delay as a phase delay, in the wideband case, you have to take Fourier transform. When you do the Fourier transform, it is true, you do get a similar relation, but it won't be omega naught here. It will be general frequency. Whatever is the frequency here, that will be frequency, omega. That means then you have to go to the frequency domain and look at specific frequencies and so on. So you can still use some of these algorithms, but in the wideband case also, right? So we are sort of right now looking at narrowband situation. So if I have a single source, and if this distance is d, so this is called the inter-element spacing, right? Then we went through this, this extra delay for this signal to get here. So compared to this signal, there is a delay tau involved, right? So compared to this signal, there is this delay involved, right? Depending on, so if these distances are the same, these inter-element delays are the same. It just depends on the angle. And we went through this. If this is d, and if this angle is theta, then this angle is theta. So this is d sine theta. The time it takes to travel is d sine theta over c. That's tau. So omega naught tau would be, omega naught is what? 2 pi f naught, right? F is c over lambda, and then d sine theta over c. So c cancels. And if you write this as the d normalized to lambda by 2, then you can, the delay comes out to be so if theta is, I replace theta by theta k, then the omega naught tau, which is this, comes out to be, I mean, if we had put minus here, this would be minus omega k. So omega k is sine theta by 2. So in general, if this is corresponding to tau I for the ith sensor, then there will be, look at here, there will be D, D, etc. So that will be, the first sensor is at location 0, second sensor is at D. That means there will be an I minus 1 term here, right? The ith sensor will be at a distance I minus 1 multiplied by D. And D over lambda by 2, I'm going to normalize it. We can call it a D, small delta or something. Or if the sensors are placed lambda by 2 apart, then this is 1. And the signal at the ith sensor is going to be just from a single source. Ith sensor is going to be what we had before. And this is going to be, there will be a I minus 1 term here. So for the ith sensor, it will be I minus 1 also. So we get, so this is due to, so let me put all the sensors together, x1 of t, x2 of t, etc., xi of t, xm of t. I'm going to call this x of t. So look at the, so this is the signal due to the kth source at the ith sensor. So when I equal to 1, for the first sensor it will be just sk of t. The second sensor will be from there e raised to minus j. There's a pi also, right? Pi I minus, you can absorb the pi with omega. What did we do? Pi is there. So pi we can absorb with omega k if you want. That may be also advantageous. So instead of writing this all the time, simply call this to be pi multiplied by I minus 1 omega k. So omega k is pi multiplied by sin theta k. And etc. So skt e to the power minus j. So we have, if we absorbed here, then it is just this. So this is omega k. This will be I minus 1 omega k. And the last one will be skt e raised to minus m minus 1 omega k. But notice sk goes outside. So then what we have is only something which depends on the geometry of the array. So this is and of course if you have k signals, then you have, by superposition, you have the summation from signal from all of them. And then you have N1T, N2T, etc. noise. So that we can, each sensor will have N1T. There is also, of course, noise term here. And let me call this to be the N of t. Let me call this to be a vector. So this is generally called, and you know the reason, steering vector. Because the omega k corresponds to theta k, right, sine theta k. So if you, as we saw last time or week before last, if there is only one source, if you multiply by the conjugate of that, then you'll essentially cancel out all this, and the SKT, which is sitting here, will sum up coherently. That's why it's called steering along. So if things are uniform, then that's the same as a DFT vector, right? Along, and that's the reason I also brought in omega k. So if you take the DFT, then when omega hits omega k, everything is going to match up, and you should get a peak, and that's the beamformer. Now let me write this in a matrix form so that. So notice that this is another way to write this will be, we can put the k here if you want, or I can call this whole thing to be AK. AK is along the direction theta k, is a steering vector. So this piece, which is this piece, I can write it in this fashion. Let's see. So in any model, when an array receives signals from multiple sources, this is the mathematical model we have, right? So like the signals I talked about, 3 different cases. Similarly, let me also tell you the different situations of noise. So of course the noise, if you look at the correlation between inter-element noise, so one situation is this. So this is uncorrelated noise, or this is the simplest case, right? So this corresponds to, write it here. So expected value of NIT, NJT, that means when I is not equal to J, the noise is uncorrelated. And when I equal to J, they all have equal variance. So this is all right. So 4 different noises. The ideal case is the easiest one, which is what we will deal with today, is when the noise from sensor to sensor is uncorrelated but equal variance. So the logic here is that sensors are not miles apart, right? Sensors are close by. So the noise situation is similar, but they are sufficiently far apart that they don't affect it. In other words, each sensor is not being influenced by the other sensor. Like crossover, etc. is 0, right? Here what happens is still the noise is uncorrelated, but it could be different kinds of sensors so that the variance on each sensor is different. So here you will have n unknowns, whereas here there is m unknowns. Here is only one unknown, the noise. Here you have sigma 1 squared, sigma 2 squared, sigma m squared, m unknowns. And then this is correlated noise, the third case. So this is correlated noise. And there itself you have two cases. Here noise is, this is the worst case. Noise is coherent, completely dependent on each other. This is the noise is only partially correlated. That means the covariance matrix will be, there will be no 0. So in this case, I'm going to call it case 1, case 2, here 3, this 4. 4 is the worst case, 1 is the best case. So if I call this to be RNN, the ideal case for the case 1 is RNN is sigma squared I. Case 2, this is case 1. And case 2 is going to be a filled matrix, right? So this entry, and it is still diagonal, so it is sigma 1 squared, sigma 2 squared, etc., sigma m squared, but rest is 0. That's case 2. And case 3 and 4, case 3 looks like this, right? So sigma 1 squared, etc., sigma I squared. But here also you have sigma I, sigma j, rho ij. This is not 0 like here, right? So sigma I, sigma j, rho ij star. And the fourth case is you have sigma 1 squared, sigma 2 squared, etc., sigma m squared. But rho is 1. So this will be rho I, rho j. There is, sigma I, sigma j. So if you want, this of course will be you can write a coherent case, completely coherent noise. So I think this is, I don't know which situation where this comes up, but we will deal with this today. So if you have other cases, then you have more variables to unknowns to estimate and so on. And if you have situations where you have coherent noise, then you have to deal with that case. So imagine coherent noise, coherent sources. Coherent noise means the sensors are sitting on top of each other or something of that sort. So that's something you can hopefully avoid. But coherent sources you can't, that may be natural. So this is uncorrelated. Uncorrelated and identically distributed. Identical noise from sensor to non-sensor. They all have the same power, etc. So let's look at the covariance matrix of this. So that's expected value of x of t, xt star. So hold on. So you understand what is happening? See, you have spatial here, and you have time here. So we are going to exploit that framework. Generally, with one sensor, all you can exploit is time. So remember, earlier when you say time series, it just output this, whereas here you also have the, so if there is any spatial structure, we should be able to exploit it this way, right? So this covariance is not on space. This expectation is on time as it is. So x of t we have here. So And if you look at here, there is nothing stochastic here. This is just unknown, this first matrix. This is stochastic. This is stochastic. So expectation will be on this and this, on the signal part and the noise part. So this is A S of t plus nt multiplied by A S of t plus nt star. Right? Star is complex conjugate. So look at this. This is a matrix. So what is this is AB, AB the whole transpose. How do what is the matrix relation? Anyone? B transpose, A transpose. So you get 4 terms, right? So you have expected value of AST plus NT multiplied by star of that, which is S star of T, A star of T plus NT. N star of T. And we'll make the usual assumption that signal and noise are uncorrelated. So that's the third complication you could bring up. So signal and noise are not uncorrelated. So it depends on how far you want to go. So I am going to assume that the signal and the noise correlation is 0. So you only have the first term and the last term. So you have expected value of S of t, ST, S star of t, then A star. And this correlated with noise is 0. So then that is just expected value of N of t, N star of t. And this is RNN. So I'm going to call this RSS, and this is RNN. So we get this and if I go to case 1 where this noise is uncorrelated, then I get so remember, this is unknown, this is unknown, this is unknown. Everything is unknown on the right side. And so you have R, right? So the maximum likelihood estimate of R, as we have seen, is you can show it to be this. So the problem is later. So first the idea is we will analyze everything assuming the ideal R. Then we can try to substitute instead of ideal R the R hat R. And then we can, because this is a random matrix, whatever is the algorithm coming out to be, it's going to be based on this. So you can see it's an you will get estimates. Then you can try to study their statistical properties, etc. But before we come to that, let's analyze the logic is, let's analyze and see. Look at here. This is even if you assume this known, this is like saying R equals X multiplied by Y. I know this, but I don't know this. How will you solve? That's our problem. Look at the right side. Everything is unknown. But we have some structure, and we are going to exploit the structure. Unlike here, if it is, of course, a scalar, then saying R equal to XY is not going to, you can't find X and Y if I just give you the product, right? But that's the situation. But we do have structure, and we want to exploit this structure. And before I erase everything, A is, here A is the direction vectors, A1, A2, etc., AK. And any AI will look like 1 e raised to minus j omega I Let's say AK is of this form, right? So everything on the right side, including capital K, is unknown. So remember, if you look at the sources, I said there are three cases. Uncorrelated sources, that means the rho ij is 0. Correlated sources, that means rho ij is strictly less than 1. And then you have coherent sources. Unlike noise, all these are possible. Each of these cases are possible. Here rho ij is 1. So let's look at RSS. What is the structure corresponding to all this? So this is S of t, S star of t, as we had before. So anybody, if it is uncorrelated, what will be the structure of RSS? Anyone? What? Huh? What about the diagonal entries? Equal or unequal? Yeah, it can be equal, but we'll assume this is to be, yeah. Yeah, so you can see the power, whatever is the, where is the transmitter? No, look at here. The model is the power of corresponding to Sk, right? Of course, if there is absorption, etc., then it is the power hitting here, right? At this stage. So otherwise, if they, what I call, not absorption, the attenuation, right? So if you know the attenuation, then you can back source it, right? So you have to take the channel loss into it.
The Sk is the received K source at the first
sensor, right. So what that's what I was saying. Wherever it is hitting first, that's your Sk. But you can translate it back to. But remember, there is no translation. We don't even know if the things are very far. The best we are going to find out is the direction, right? Then, of course, you can do a triangulation. If you have another ship or another set of sensors here, then you can find those and then find these angles and find those angles and figure out where they are, right? Or an L-shaped antenna, whatever. So how about the second case? How will the correlated Rij look like? It will be, so the R will be a busy matrix, right? All filled matrix. So this will be still P1, P2, etc., Pk, but this will be Pi, Pj, as you said, square root of that rho Ij. So all the, and how about the last case? So the best way is, if it is coherent, the easiest example is multipath. You have a signal which is coming here, let's say S1, but then it also gets reflected from elsewhere. So you have different angles, and this also goes and comes back, etc. So each place there is some scattering going on, there is some loss, this and that. So, but the sensor is seeing only this. So this is your Sk, right? But you can see, compared to this, what happens is the same signal comes back a little later attenuated, isn't it? So if you look at S vector here, the first one is S1 of t, second one is delayed and attenuated version of the first one, etc., right? Delayed and attenuated version of S of t, right? But remember, delays are these are not the same delays. These are whatever is this path. So, but the delays will come out as a phase. So you should be able to see that this is of this form, right? So it's just a complex vector which has got some magnitude which will correspond to the refraction and scattering density here, and also the phase part which will correspond to the delay. So let me call this to be, so in that case, let me correspond this to be alpha. So in the third case, you can see this will be simply some P naught multiplied by alpha alpha star, right?
Sorry. The index for the alpha should be K.
Yeah. No. Remember, this is.
Have K sources and M sensors.
Yeah. So what I meant here was this is at each sensor. I mean, we are looking at. What did you say?
Nothing. I thought you were mentioning that we have like K sources, which we are saying that each of them is a shifted.
Yeah, right. You're right. So this is S of t.
But the index should be K because they have K sources, right? We don't care how many.
Yeah, right. I mean, we can have any number of, but if we are using the total returns to be K, you are right. Let me write it as K. We want to respect the same terminology, right? The number of signals are K, right? So this is going to be alpha alpha star, right? So look at here. What is the rank of this matrix? Anyone? This rank is K. This rank? K in general. And this rank? 1. So you have to realize, even though there are K sources, the rank could be different. It could be either 1 or full rank. Now, you can of course have in between also, because all coherent doesn't mean all the sources have to be coherent. Some of them could be coherent, right? Some of the sources could be coherent. So anyway, so what we are going to take is the rank is going to be, this is rank, okay? Rank is going to be between 1 and, rank cannot be 0, that means there is no source, right? So rank is strictly greater than or equal to 1 or less than or equal to K. So if the rank is equal to 1, then this is coherent, right? Completely coherent, right? Completely coherent, and then you can have partially coherent, which will be somewhere in between, right? Any questions so far? So if it is, look at here. So if it is completely, so let's go to the easiest case, which is the easiest or whatever, or the best structure is RSS is diagonal with the unknown diagonal entries, but all the off-diagonal entries are 0, so that it's a full rank K. Look at here. What is the size of capital R here? M sensor, so that's M by M. So A is, you can see, A is M by K. This is K by K. This is K by M. So this whole thing is M by M. So what is the rank of this piece? So the sigma squared, this is easy. The rank is N because it is diagonal. What is the rank of this piece? Anyone? At most? M, Mary? Oh, so let's look through this. This matrix is size M by K. We will assume that K is less than or equal to M. Then, so long as these columns or these direction vectors are not everything is on the same direction. These are all independent vectors. So what will be the rank of this? That will be rank, K will be rank, because the rank is, the first rule is rank is the minimum of, less than or equal to minimum of M comma K, right? So rank cannot be greater than, if the number of columns are less than the number of rows, rank cannot be equal to the number of rows, right? It has to be less than or equal to the number of columns. And of course, if the columns are linearly dependent, then the rank will collapse. So let's assume the best case that none of these sources are along the same direction, collinear, so that the directions are different. Then this rank is K. And the middle piece, you see, so if you go to case number 1, the middle piece, the rank will be K. And this is rank K. So what is the rank of this? Well, how do you know so quickly? What about this? If A and B have rank AB, what is the rank of AB? Anybody? Let's say the rank of this is, so this is, let's take the same thing. Rank of A is M, rank of B is N. Then what is the rank of AB? So there are rank inequalities. You have to.
But if A is full rank, then you can say something.
But A is not, A is full rank, right? But A is not square, so you can, A is, yeah.
If are non-zero in that case, if the RSS is diagonal and DKs are non-zero, then you can say that it's
Yeah, so it goes like this. There is Sylvester's inequality. If you take a product, rank of AB is what? Rank of A plus rank of B and minus the common size here, right? So is greater than or equal to, you have, first of all, the trivial inequalities, rank of the product is less than or equal to, look at this, if the rank of this is M, rank of A is M, rank of B is N, then rank of AB is less than or equal to minimum of M comma N. Then the other way is, I believe it is, and remember, if you multiply two matrices, they have to have a common size, right? So this is M by K, this is K by N, K by something, right? And the Sylvester's inequality is rank of AB is greater than or equal to M plus N minus the common size. So if you use that, you can actually show that, you can quickly see that this piece is rank K if it is fully rank. And this is diagonal. If you add both are non-negative definite matrices, right? Look, this is non-negative definite. Why? Why is this non-negative definite? The first piece.
because of the symmetry of RSS and
No, because RSS is non-negative definite. Why? Because look at here, RSS is a covariance matrix, right? So if you multiply by any vector transpose, that's non-negative. So that's being multiplied by the same thing, so the same logic goes. This is non-negative definite, this is non-negative definite. So if you add two non-negative matrices, you cannot decrease the rank. In fact, this being diagonal, this is full rank. Yes? So to this full rank, if you add a piece, its rank is not going to decrease. No, hold on. Forget about this piece. This is positive definite, right? Then you are adding a non-negative definite piece to it, because look at this. The size is M by M and its rank is K. But when you add this to this, what is the rank of the whole thing? That's what I'm trying to add.
M.
Rank is M, yes? Or where is the confusion?
Why is the rank M then you have?
All right, forget about this. What is the rank of this, just the noise covariance matrix? M. To that you are adding a non-negative definite piece. Rank cannot go down, right?
Think about the eigenvalues. The eigenvalues of that guy can be positive or zero, and then you're adding sigma squared to them. So they all will be positive, right?
How do you think sigma square is eigenvalue change?
I mean,
Oh, so-
like the eigenvalue decomposition of that, as Q, right? And then plus Q, and then you're adding sigma to the eigenvalue.
Oh, let me explain to you what he said. If consider this matrix, let me call it R1. Okay, that's the signal part, right? So this is a non-negative definite matrix, right? Its rank is K. We just figured out. In this case, we are considering this case or this case, either way. So long as the middle piece has rank K, so I think that this is the, if I remember right, this is the inequality I want to use. All right, so you can apply this. See, we know that, so go 2 by 2 cases. So take this product, that's the way you go. So each of them has rank K, right? This has rank K, this has rank K. So let's apply the second inequality. K, and its common size is K. So it says the rank of this product is greater than or equal to K plus K minus K. So greater than or equal to K, right? So apply the first inequality. Each of them has rank K. So its rank is going to be less than or equal to minimum of K comma K. So rank is less than or equal to K, rank is greater than or equal to K. So the rank is going to be equal to K, this product. Then you do the same argument here. This has got rank K, this has got rank K. The common size is still K, and again apply that, you'll get the whole product to have rank K. Knowing that, once that is done, as he says, let's do the, I went through this last week. If you do an eigenvalue decomposition, it will have, all the eigenvalues will be, whatever, it will have non-negative, all the eigenvalues will be non-negative, right? But there will be only K non-zero eigenvalues. And yeah, the rest of it is, rest of it will be 0. So there will be m minus k 0 eigenvalues. And let me call them to be mu's. Okay. So this is for this piece. So these are strictly, all these mu k's are strictly positive. And consequently, if I call the corresponding eigenvectors u1, u2, uk plus 1, etc., um, then you know that this can be written in this form. Right? Where u is u1, u2, uk, u. Okay, so that's the first consequence. Remember, we haven't used anything other than the fact that they are just uncorrelated signals. So let me bring in R. This is what he was trying to say. R is what? R is the first part. ARSS A transpose plus sigma squared I. Remember, U has the property U star is I, right? It's a unitary matrix. All these vectors are orthogonal and of unit norm. So look at here. First piece can be written. So let me call this to be lambda. This is lambda. This is U star. Then you have sigma squared I. Look at here. I am going to write it as U star. Then U I can pull out, and this is what he was trying to say. You have mu1 plus sigma squared, mu2 plus sigma squared, mu k plus sigma squared. But then after that you only have sigma squared, sigma squared. Yes, this is what you. So we know that if there are k is unknown. Look at the logic. But we know that when we do the eigenvalue decomposition, lambda, if you look at the eigenvalue, if you call this to be lambda 1, lambda 2, lambda k, etc. We know lambda 1 is, and we can arrange it, is greater than or equal to lambda 2, is greater than or equal to lambda k. But then after that, that's going to be greater, the rest of the eigenvalues will be equal to sigma squared. So the total number of eigenvalues are known because there are only m eigenvalues. Okay. So this gives us the clue. This is the high resolution clue. So if there are, you plot the eigenvalues. So you may have eigenvalues will decrease, but after a certain stage, the eigenvalues, look at here, are going to be all equal. So you plot the algorithm is you plot the eigenvalues where they, go from this end, where they see how many of them are equal. That will give you m minus k. M is known, so you can solve for k, the number of sources. So k, this will be, so this will be your k. Now what? So the first problem is solved. K is known. So you look for this flat piece. So this is why I said earlier, this technique is only going to work if the number of sensors is more than the number of sources. So if you have 100 sources and 25 sensors, this is not going to work. It needs to be the other way. So the first condition is that m need to be greater than or equal to k. It need to be strictly greater than k, because you at least, even that's not enough, because if m is k minus 1, I mean, if k is m minus 1, then the last eigenvalue you will not know whether it is, except, so at least m need to be greater than k minus 1. Strictly, you need at least two values equal, just to get an idea, right? But the bare minimum is what I said, yeah?
Can be 0, equivalent is 0.
What is it? K is 0?
Yeah.
K is?
No, m is equal to k minus 1.
M equal to k minus 1, look, the problem is, of course it will work. You will only have one sigma squared. How will you know whether it is sigma squared? You have no idea what is, unless you know the value of sigma squared earlier. You will not, there will be no repetition, right? That will be the case. All these, the eigenvalues just keep decreasing, etc. So there is no flat case. Every eigenvalue is greater than the other eigenvalue then. Then of course you can take a good faith saying that the last one must be, it may or may not work, right? Yeah, some in between, later also look at here, some of these, but even then, so the key is here. Some of these could be equal, but there has to be a jump from here to here, unless this, I think I erased, so, see, I wrote it here. This cannot be equal here, that's the key. Where the jump happens, there will be a jump, and after the jump it will be all flat. So to observe this property, you need the flatness. For that, at least you need 2 eigenvalues, I'm saying. But bare minimum is the first condition. M must be greater than K. That's necessary. This is necessary. Yes? All right, then what? So you found K. Yeah, we are almost over with this first concept. So I'm going to, so remember the eigenvectors are u1, u2, uk, then uk plus 1, etc., um. These are corresponding to eigenvalues lambda 1 through lambda k. And these eigenvalues are corresponding to noise eigenvalues. So I'm going to call this to be, remember these are vectors spanning a whole dimension. So I'm going to call this, going to separate this into a signal and noise subspace. It makes sense because these vectors correspond, these vectors definitely correspond to the noise covariance matrix. So we can call it the noise subspace. So the complement of that should be signal subspace. So it's the whole space we are decomposing as in this form. Right? So you have so that's sort of the, this is the idea. Then you have an orthogonal space which is uk plus 1, etc., um. And look at this. Both these vectors are we have in our hands. These vectors we have in our hands. So the whole space is decomposed into, so this is your signal subspace, this is your noise subspace. So you are, what do you mean by 2 signals have, see this is the signal covariance matrix, right?
Any signal, sorry, I mean eigenvectors. 2 eigenvectors, eigenvalue, will they still be orthogonal?
All right, so so there will be 2 vectors. There will be a subspace with a 2-dimensional subspace for that. In a 2-dimensional space, you can choose 2 vectors to be orthogonal. First of all, let's if two eigenvalues are unequal, the corresponding eigenvectors are orthogonal. So let's say the first eigenvalue has u1 is the orthogonal. The second one has second and third are equal. Mu2.
Just think about identity. All the eigenvalues of identity are 1, and all the vectors are orthogonal.
Right, hold on. So the similar to that. So I'm saying lambda 2 and lambda 3 are equal. Then there will be they will span the eigenvectors will span a 2-dimensional subspace, right? Right, there will be 2 vectors in that, but so you have freedom there. But any vector in that will be orthogonal to the first one, u1, right? Then you can see that in a 2-dimensional space, I can forcibly choose 2 vectors which are orthogonal. Then they are by definition orthogonal to the other one. So by design, I can make them all of them orthogonal. Okay. I manufacture in this aspect. So that's how I manufacture at the end also. Right? So these vectors are known. Then look at the property that is going to come out. So you have R equal to A RSS A transpose plus sigma squared I. So I'm going to do this operation deliberately. I'm going to multiply the covariance matrix with one of the noise eigenvectors. So what I'm going to do is one from here, ui. So this will be A RSS equal to what? Anybody? What is the definition of RUI? Sigma squared UI by definition, right? Then you see this and this cancels. So you get the equation that A RSS A transpose UI is 0. So that's the first. This is true for I equal to any one of these eigenvectors from the noise subspace. So we have A RSS A transpose UI equal to 0. What can you conclude at this point? Anybody? UIs are in the noise subspace. UIs are known. Nothing else is known. Oh, so from here, what can you conclude? Remember, this I is from the red space, which is the noise subspace. I equal to k plus 1. Could be k plus 2, etc. up to m. So if immediately you can't conclude anything. So suppose I multiply here with A star. That's the same as multiplying by A star. Nothing has happened. So what is the size of this? Anybody? A is what? Remember, A is here. A is m by k. What was A? A is, of course, A1, A2, etc., AK. So A is m by k. What is the rank of A? K. So what's the rank of A star A? K. Silversted's inequality. So that's full rank. So a full rank matrix multiplied by something equal to 0. What can you conclude? Because, you are right. So you can multiply, that the way is you can multiply by the inverse without, because it is full rank, you can multiply with this inverse, yes? So then this multiplied by this is identity. You multiply A star A here, yeah.
Can you directly conclude that RSS UI is 0?
Maybe not, because what if this was lower rank?
No, because like RSS is positive semi-definite, right?
Yeah.
And we know that if x.
No, but if originally A is lower than rank K, that argument won't work.
Any vector, I mean, if you put any vector times a positive semi-definite matrix, let's say like B is positive semi-definite, so Bx star is 0 gives you that Bx is 0. Oh no, yeah, my argument is wrong. Yeah.
So you need this to be full rank. You need this to be full rank, which it is. So we can get rid of that. So this now reduces to RSS A star UI equal to 0. Now what can you conclude? If RSS, look at here. Here you have 2-3 cases. We haven't used the RSS structure. So if I'm saying RSS is rank 1, then you can't conclude anything there. So let me go to this case. RSS is full rank. If RSS is full rank, I can multiply by the inverse of RSS here. So then you get the equation that this goes away. Then you get A star UI equal to 0. So A star is what? Look at A star. A1 omega for A omega, A omega 2. A star is, the vectors are now put this way, multiplied by a eigenvector from the noise of space equal to 0, I equal to k plus 1, etc. up to m. So look how many conditions you get. First row into first column. Look at here. So you get so many equations. This is what. So what happens is the unknown. This is the key result. The unknown directions of arrival are orthogonal to the known noise of space eigenvectors. So this is true for k equal to 1 through k. K at this point is known. I equal to k plus 1, etc. up to m. These are known. Omega k's are not unknown. So what we could do is you could plot this. You could take a generic. You could plot this quantity with omega as pi sine theta, unknown, right? So we know that, look at here, we know that when you plot this, or we can, generally what is done to amplify this will, of course, then what happens is the first algorithm is when omega equal to, so p omega k's are zeros, right, by definition. So when you scan through all the omegas, when omega hits omega k, this is going to go to 0. So if you plot q, which is 1 over p, you should be able to, this will pop up like this, right? At theta 1, theta 2, theta k. In fact, we can, this is, look at here, we haven't exploited all the eigenvectors. This is true for k plus 1 through m. So of course this is true even if you sum up over all the eigenvectors. This is over all the noise eigenvectors. And so the rest follows. So the p is either corresponding to one eigenvector or including all the noise eigenvectors. Yeah, right. Index of summation, very good point. Index of summation should be k plus 1 through m. At this point there is no issue because k is already figured out from the eigenvalues. So this is called the multiple signal classification or music algorithm. Multiple signal classification. I mean, there are several variations of this algorithm called root music, and then you can do the statistical analysis, etc. But at least in the main case, when the signals are, so you can see this argument will also go through in the number case too. If so long as the RSS is full rank, whether it is completely correlated, completely uncorrelated or partially uncorrelated, so long as RSS is rank k, this will still you can operate, and this will be true. So this will not be true if RSS is not a full rank, and that's the problem that we want to look at it next. So to summarize, if the signals are partially correlated or completely uncorrelated, then the eigenvalues will drop, will be equal beyond the number of sources. So k you can determine from the eigenvalue plot. And then the eigenvectors corresponding to the sigma squared or the noise eigenvalues are orthogonal to the direction vectors. That's the key property. Eigenvectors, these are the noise eigenvectors. And these are the directions of arrival. So directions of arrival and the noise eigenvectors are orthogonal. So you exploit that property one way or the other way to figure out the sources. That's actually this algorithm, these are from, not exactly in this case, but these properties are very well known, I think over 50, 70 years from the spectral estimation work and so on. So these are rational systems, but with the decay coefficient equal to 0 or pure sinusoids. And this is one way to find out the, okay. So finally, once you find, going back to this equation, look here. So once we find out this is known, sigma squared we figured out, then to find out RSS, you can see what you need to do. So let me write that step and conclude with that. So this way you can determine theta 1, theta 2, etc., theta k. That gives you R. So if R is known, and sigma squared we found out earlier, so you do R minus sigma squared. So that's equal to A RSS A transpose. Then I multiply by A transpose here, this becomes A transpose. I multiplied by A here, this becomes A. So I do A transpose A inverse A transpose R minus sigma squared I multiply by A transpose A inverse, that gives you RSS. So you can estimate the signal covariance also. So in the original problem, everything was unknown. Now finally we figured out everything. We figured out K, the directions of arrival, and also the source covariance matrix. This is assuming, only assumption is either the sources are like this or like this, but not completely coherent or even partially coherent. Sigma squared is evaluated from here. Eigenvalue. So you have to use both so everything that need to be exploited has been exploited. Okay.